Hello. So this marks the last session of this week and also the last session of this Keldysh field theory lectures by Professor Alessandro Silva. And over to you right now.
Thank you. Okay, so as I promised, today we are going to derive the Boltzmann kinetic equation starting from a quantum model that I wrote down yesterday. So my quantum model is this. I can write it in this way. Plus B of x plus U of x and R T psi x. So these are fermionic operators. So they satisfy standard anti-commutation relations. Then I have here a Gaussian random potential. So the Gaussian random potential is a random potential that has zero average, and the variance is given by 1 over 2 pi density of states times tau times delta of x minus x prime. I will explain later on why you have to put here density of states times tau. For the moment, let's leave it as it is, okay? You will see why I'm using this parameterization. And then U of x and t is an external potential that has a typical time scale, typical spatial scale, and length scale, and a typical time scale T naught, which are both R naught much larger than the Fermi wavelength, and T naught is much larger than 1 over epsilon Fermi. And therefore, I have that the conditions of, I have a separation of scales that will allow me sooner or later to do an adiabatic expansion. Moreover, I will consider this problem in the limit in which kf times L is the mean free path, is much larger than 1. So this is the limit in which I can deal with disorder perturbatively. So I can do a perturbation theory in terms of this potential here. Now, L here, I did not define it, but is Vf times tau. And Vf is nothing but, and tau is nothing but this parameter. So at the moment, this identification of this tau with the mean free time is not obvious, right? We'll have to do some calculations. But it is the mean free time. So, and then once you have the mean free time of standard Drude theory, you can construct the mean free path in the usual way. So now the question is, what do we do with this? Well, the standard procedure is it's a non-interacting problem. We can, for example, think of doing perturbation theory in both V and U. So we can crank up the machinery, the standard machinery, and for example, compute our contour-ordered Green function of our fermionic operators. And this is going to be given by this, plus you will have diagrams in which you put a wavy line. So the wavy line is an insertion of URT, plus diagrams in which you put a dashed line. Dashed line is an insertion of E of x. And then, well, you put as many lines as you want. I mean, you will just throw them down one by one in all possible combinations. Okay? Sorry? V and U. I mean, can I have a line which represents the multiplication of V and U? No, because they are summed up there. So whenever you will take down from the exponential, from the time-ordered exponential, you will take down terms, they will act one by one. So for example, you will have terms like this one, terms like, I don't know, this one, etc., right? And now, so now the problem is that this is a disordered potential. So we are not interested in properties of a single disordered realization. As usual, when we have disorder, we want to consider the average with respect to disorder of our physical quantities. Now, the Green function by itself is not a physical quantity. The Green function is, different times is an amplitude, but it's not, strictly speaking, a physical quantity. Depends on the gauge. It has many problems. But still, here I will be interested in writing a kinetic equation, which is an equation for the Green function, the statistical Green function at equal times. And that is a physical quantity. It tells me what is the number, the occupation of my particles. So all this to say that it makes a lot of sense to average over disorder this expression. And these brackets mean average with respect to the statistics of V, okay? And let's see what happens. Well, if I average over disorder this, nothing happens. This, nothing happens. This one, well, gives me 0, right? This is equal to 0. This one will spit out the delta correlator. So it will give me something like this. So this represents the contraction of two insertions of V. Sorry, I have to use different fingers. The contraction of two different letters of insertions of V. So V of x prime, you contract them, and you get this expression. So this is what it represents. This one, I will get 0. So this is because it has only one line. In general, all diagrams in which I have an odd number of lines will give me 0. And then, of course, I will be able to generate all sorts of diagrams. For example, these ones. So if I go to next order in the disorder, I will have diagrams of this type, diagrams of this type, diagrams of this type with a wavy line somewhere, etc., right? So that's what I will generate. Now, the point is that this is a problem that was studied a lot in the 50s and 60s and 70s and 80s of last century. It is the problem of propagation of electrons in a disorder, of non-interacting electrons in a disordered potential, was studied a lot perturbatively because it gives you a way to study what happens to, so to study how localization, Anderson localization, which is what happens when you put a lot of disorder in an electron system, develops as you increase slowly the amount of disorder that you put in your physical system. And in particular, what you can think of doing is computing the so-called weak localization corrections to the conductivity and all sorts of disorder-related quantities. This is a topic about which you can read in the book by Abrikosov and Gorkov. Then you can read about it in a very nice paper by Boris Altshuler. It's in one of the Les schools. I don't remember which one, but it's called mesoscopic physics. So just look for mesoscopics. And then there is, of course, the book by Efros and Shklovsky. So in this order, because, well, this is a nice book. I like it, even though it's very much outdated. I mean, it's a very old book. This is a very nice review, but it requires some, some knowledge of the machinery. This is a very comprehensive book that includes also various stories about localization, etc., but it's pretty much, in my opinion, hard to read. So it's quite complicated. Now the story is, so without any explanation, the story is these diagrams are not all the same. It turns out that using the large parameter KFL, much larger than 1, which creates immediately a small parameter 1 over KFL, you can prove that all diagrams that have crossings at a given order in perturbation theory, all diagrams that have crossing have an additional smallness in this parameter as to compare to the ones that do not have crossing. Now, this is something that happens quite frequently, for example, in 1 over n expansions in quantum field theory. Never mind. It's, yes. Well, there is nothing to understand. I'm just stating it. So it's I'm saying whenever, if this is small, whenever you see a diagram that has two dashed lines that cross, this diagram, as compared to this one, has an additional smallness of 1 over KFL. So in other words, this is much small, sorry. It's like that, so you can neglect it as compared to this one. Right? So it's a statement. I'm not going to prove it. And therefore, what happens is that you can, in practice, the absence of these diagrams tells you that you can resum this whole Dyson series in something that is known as a self-consistent Born approximation. So you can write this as you see? Well, here I'm for the moment. So if you want to put also back the external potential, you have to put it explicitly. But this is called a self-consistent Born approximation. It is the same as the self-consistent Born approximation that you use in scattering theory. And it's just telling you that your self-energy is going to be equal to this plus this plus this plus. So people call these sunrise diagrams. It's a pretty obvious. People like to give names to diagrams. It's a dangerous thing to do. You never know. Anyway. Yeah, so that's what you get. And now the question is, okay, so can we, let us try for simplicity to consider the case in which we don't have an external potential. Which ones? This, that. Well, but these are not, I mean, it's not three kind of diagrams. This is a self-consistent equation that has a self-consistent Dyson equation that has a self-energy that has an infinite amount of diagrams, right? So it's a pretty tricky object. Again, you use diagrams and you recognize that this is the structure, but this is not as simple as the non-interacting system we have been dealing with. The dashed is that correlator there. So the dashed is the disorder correlation. So if this is x and x prime, this is v of x b of x prime times g of x and x prime. Right. So now that we know this, let's take u equals 0 and see if we can understand a bit more in detail what is going on here. Now, if we take u equal to 0, then it is pretty obvious that that your Green function is going to depend only on time differences and position differences, because the system is translationally invariant both in time and space, right? And therefore I can take Fourier transforms. In particular, I can write down the Dyson equation for the retarded Green function. We already know that we can, you can easily interpret these diagrams in terms of contour-ordered Green functions. We will do that. But even if we interpret them in terms of contour-ordered Green functions, at the end of the day, the translation, by now we know how to do it easily. So if we want to, yes?
If you don't disorder average.
Sorry?
If you do not perform disorder average.
Yeah, well, then you suffer.
But you won't get a Dyson equation.
No, you will not. But then you have to ask yourself whether it makes any sense what you're doing. Because if you don't disorder average, then you're looking at, so each physical quantity you're looking at depends on the specific disorder realization you're inserting. Which is, it makes sense if you want, but again, so, I mean, isn't it, then you can start asking me the question, well, what the hell, if I ask an experimentalist to measure the conductivity in a certain sample, he's not doing the disorder averaging. He's just measuring the conductivity of that sample. But the point is that typically physical quantities are self-averaging, right? In particular for large systems. Now, then, well, you can have situations for mesoscopic systems in which this self-averaging is not there anymore. There are what is known as mesoscopic fluctuations, which means that the sample-to-sample fluctuations of the conductivity are not insignificant anymore. But, this requires your system to be small, here we are considering systems in the thermodynamic limit. So all of this to say that, if you don't want to average over disorder, you're free not to do that. But then you have to think about how specifically you compare to experimental data. So in my opinion, it makes much more sense to average over disorder and then eventually study the fluctuations with respect to the statistics of disorder of your physical quantity and see how the probability distribution changes. Instead, if you don't average, you're just looking at a specific instant. It's like saying, okay, I'm interested in seeing what happens when I throw a dice. Right, so you can do that, but if you're a physicist, you're interested in the probability distribution. Okay, so is it clear, my answer? Right, so it's time translational and space translational invariant, and the retarded Green function, when I have convolutions, and here I have a bunch of convolutions, is going to be the product of retarded self-energies, Green functions, etc. So I immediately know how to translate this into something retarded. This is what it is. Where the self-energy sigma is nothing but so this guy here is this. So is 1 over 2 pi mu tau. And then here I will have delta x and x prime. So therefore this will spit out sum over p, will spit out a Green function at equal position, at equal points in space, which is the sum over all momentum indices sum over p of g retarded p omega. Okay? The sum over p comes because it's g of x, so the difference is equal to 0. Right, so, well, then you look at this, it's an algebraic equation, but it's still not a straightforward equation to solve. So what you do is you make an ansatz. You say, aha, wait a second, let me say that this is equal to minus I times gamma, right? Sorry? Oh, the third term I said that I set u equal to 0, right, and there. So I just neglect it. You're right, in principle it's there. Right, so in order to solve this equation, let me set it equal to minus I gamma. And then what I get is g retarded p and omega equal to 1 over omega minus epsilon p plus I gamma, right? So this is my green function. I solved that equation for g retarded, and that's what I get, a simple pole. And now I have to solve self-consistently for gamma, so I have to put this in here, take the sum, and figure out what is gamma. So the sum is sigma retarded is equal. So I do the usual trick. I pass from the sum to the integral and assume that the density of states is constant. In this particular case, it makes sense because I'm I'm interested in electrons close to the Fermi energy, which typically have a linear dispersion. So then I say, well, this is 1 over 2 pi mu tau. Then I have density of states integral d epsilon p. And then I have 1 over omega minus epsilon p plus I gamma. And then I look at this and say, well, look, it's now I can use the Cauchy formula. The Cauchy formula that tells me that this guy here is the principal part of 1 over omega minus epsilon p minus I pi delta of omega minus epsilon p. No, bullshit. Okay, this is going to be broadcasted in the entire universe. It's wrong. What I just said is wrong. You do this integral by contour integration, right? So then you don't have to use Cauchy formula. And if you do this integral by contour integration, you close your contour above, and then you will get minus I pi times 2 pi tau. And, well, this is equal to minus I over 2 tau. So this is equal to minus I gamma by definition of gamma, and therefore gamma turns out to be equal to 1 over 2 tau. Okay? Who? Yeah, so this is the self-energy that comes because of the disorder. Yes. Yeah, so here in principle I should have minus sigma r. And then I'm saying, well, look, this is equal to minus I gamma, so plus I gamma. Then I plug it in this expression, I do the integral, and that's what I get. So what I discover is that gamma is equal to 1 over 2 tau. And now my claim is that this implies the fact that G retarded P and omega is equal to 1 over omega minus epsilon P plus I over 2 tau implies that tau is the mean free time. Which can be interpreted as mean free time. Why? Because if I take the Fourier transform with respect to omega, I'll get a G retarded at T P to be equal to minus I theta T minus T e to the minus I epsilon pt, and then e to the minus t over 2 tau. Now this is an amplitude, is not a probability. The green function is an amplitude. It's an amplitude of doing what? Is an amplitude of creating this particular one, of creating a particle of momentum p at time t equals 0 and destroying it at time t after it, right? So in order to destroy it, you have to find it. If you don't find it, you don't destroy anything. So in a sense, it tells you what is the amplitude to find a particle with the same momentum, with the same quantum number after time t. And you see that this amplitude is decaying with e to the minus t over 2 tau. Now, if you take the absolute value squared that will generate a probability, you will get a decay with tau. And this gives you this kind of interpretation of tau as mean free time, because it tells you, okay, so it's essentially the time scale that controls the decay of the probability of finding the particle with the same momentum. And this is exactly what Drude tells us, right? Drude tells us, okay, well, you have your particle that is moving there with a certain momentum. At some point it encounters, with a mean free time, tau, it encounters an impurity, and then the scattering is isotropic and the momentum gets randomized. So it's the same story, okay? All right, so now given this, we can now proceed to consider the non-equilibrium situation. So now we put back how's it called, the potential U, and now we try to study the system. Now I'm going to teach you a trick now. The trick is a trick to write kinetic equations. Now, what is a kinetic equation? A kinetic equation is a derivative, is an equation typically for a statistical Green function. Now, here, for the sake of being pedagogically clear, I've been using all these lesser, greater, retarded, advanced Green functions. They are not needed really, because they are not all of them independent. Only 3 of them are independent. So typically in the literature, people use 3 Green functions: retarded, advanced, and the Keldysh Green function that is a combination of lesser and greater, and write down a kinetic equation, which is the equation of motion for the Keldysh Green function. Well, in our language, it's going to be the equation of motion for G lesser. I'm not going to introduce the Keldysh Green function. I advise you, now that probably you understand everything about field theory and Keldysh, just pick the book by Kamenev, read it. It's a wonderful book, everything explained with the formalism as it should be in the most general form, okay? So with that, you can do whatever you want. This said, so the kinetic equation is an equation of motion for this. Now you see that when I take a derivative, well, the derivative will act twice, will act on the left and will act on the right. So in order to write down the kinetic equation, therefore, I have to take into account this symmetry. And therefore, what I do is I write, first of all, I start with the Dyson equation, which we already know what it is. So it's this one. And then I write the same Dyson equation, but I write it in a different way, which is equivalent, because you immediately realize, if you think about it, that they are the same equation. Okay? So you see, this is one, this is the other. And now what I do is I act. No, this is a mistake. I act in this equation on the left and in this equation on the right with the differential operator that is the inverse of this guy. So in other words, I I introduce an operator G naught to the minus 1 that is acting on the left, that acts on G naught, and produces for me delta of t minus t prime. And then I introduce the same operator that acts on the right and is delta of t minus t prime. Now here you have to worry about it a bit. So what is G naught to the minus 1? Right, so this is the identity. We know already that lesser and greater that are, okay, so these variables here are defined on the contour, on the Keldysh contour, right? We know already that, so therefore this delta function is equal to 0 if t and t prime are sitting on different branches of the contour. Now, we know perfectly well, in that case, G naught is a lesser green function because I'm sitting like that, or it's a greater green function because I'm sitting like that. Now, you remember that if this is a lesser green function, the differential operator that was killing it was I dt minus grad squared over 2m. This is what we used, the equivalent in this problem of what we used to kill the G naught lesser when we dealt with, in a second lecture, perhaps. Right, so this is G naught to the minus 1 acting on the left. What about the guy acting on the right? Well, the guy acting on the right is acting on t prime, right? Because it's taking the derivative with respect to the second index. But t prime as a dagger operator, because this green function is psi t, psi dagger t prime. And therefore, the operator that kills it is going to be minus I dt prime minus grad squared over 2m. And this is G naught to the minus 1 acting on the left. Okay? All right. And well, here it's important also to keep track of the positioning. So this is x and this is x prime. Right, so now that we understand this, we are ready to crank up the machinery. So we look at the Dyson equation that we wrote up there. We know that acting with these operators will produce us deltas. And now we the camera should be moved. So you see only that blackboard. In the movie, you will see only that blackboard. It's automatic? Because I see here a video. Yeah, it's okay? Okay, good. Because here I see a video of myself. I see myself only there. Okay. Anyway, so now you act on the left and on the right with these differential operators. Yes?
So when you didn't have this U-turn, you had the first U-turn,
Yeah.
then why didn't you consider this?
Well, in that case, look, first of all, in that case, it's not important to write any kinetic equation because it's a non-interacting problem without any drive. It's time independent, so you know essentially everything about it. So you don't need to compute. So let me put it this way. If you don't have a drive, if you put a particle with a certain momentum, that's a certain energy, it's not going to move, right? So you give a certain distribution, and that's it. That's the distribution. It's not going to change. And therefore, it doesn't make any sense to write down a kinetic equation. it is actually a waste of time. So that's why I didn't even attempt to write a kinetic equation in that case. But if you have a time-dependent potential, then the distribution can change, and therefore it makes sense to write down something like a Boltzmann equation. Okay? All right, so now I take G naught to the minus 1, I act on the left, and G, and then this is equal to, so schematically, I'm writing things schematically, identity plus UG plus sigma G. So you see, I'm acting on the left, and when I'm acting on the left, I'm simply erasing all the single lines, right? Because that gives me a delta function. And here, just for the sake of simplicity, I'm writing the deltas as the identity. So I'm thinking about this as being matrices on the Keldysh contour. Why am I doing so? Well, first of all, because I don't want to write integrals all the time. It takes too much time. And second, because these are essentially matrices. You know, whenever you see a convolution, it is essentially a matrix product. And whenever you see a delta function, it is essentially an identity. Well, that is a delta function on the Keldysh contour. It is the identity if you just take your Keldysh contour and you discretize it into small pieces, which is, by the way, what Kamenev does to derive the path integral. So all of this to say that as for the path integral, it makes a lot of sense to think about everything in terms of matrices. Okay, so then I act on the left, and I will get identity plus GU plus G sigma. And now what do I do with this? Now what I do is I take the lesser, I'm not interested in equations of motion for retarded Green functions. Those I know how to solve. I mean, I'm interested in the kinetic equation, which, as I told you, is the equation of motion for the lesser Green function. And therefore, I specified both these equations, which I wrote down formally here, for the lesser component. Okay? So I do the translation. And the translation is G naught to the minus 1 G lesser equal to, well, the identity lesser. Well, the identity lesser, the two guys are sitting on different branches of the Keldysh contour. And therefore, the delta function is going to be 0, right? So forget about it. This is 0 plus. And here I will have to go U G lesser, because U is just a function. Is not there's no convolution here. And then you will have plus sigma lesser G advanced plus sigma retarded G lesser. And similarly, you will have G lesser G naught to the minus 1 acting on the left equal to 0 plus U G lesser plus, well, G lesser sigma advanced plus G retarded sigma lesser. And now what I do is I take these two equations, I take the difference, and then I set the times equal. And when I take the difference, you see, when I take the difference, because of this minus sign, I'm taking the difference of the minus sign that is sitting here. When I take the difference and I set the times to be equal, it is equivalent to taking the derivative of G lesser TT, right? So you're taking first the derivative with respect to the other, then plus the derivative with respect to the second argument, and then you take the two times to be identical. Okay? So that's why I'm taking the difference and not the sum. Clear? And this trick is always there, right? You compute, you take the derivative on the left, the derivative on the right, and then you take the difference and you make the times equal. So whenever you want to, well, I'm not sure I will get there, but There is another interesting problem in which you can use this trick to derive kinetic equations. In general, no, because the potential is time dependent. The potential is in general is a time dependent potential. If it's not a time dependent potential, then I mean all this story is not particularly interesting. Sorry? What do you mean by going around one direction of time? I don't understand what you mean. Oh, you mean on the Keldysh contour? No, no, you don't want to do that because, well, because it's against the spirit of the mechanism, right? So the story is, in general, what you want to do is to write formally the equations of motion or anything, or your diagrams, or everything you want on the Keldysh contour. And then you do the translation at the end. At least this is the way I taught you. You can do better if you use the mechanism by Kamenev, but this is what I taught you, what we are following here. So first we formally write all the equations of motion on the Keldysh contour, and then we proceed. So all of this has to be, you cannot think separately about the two branches. Everything is written on the Keldysh contour, and then at the end you translate. Okay, so now we take the difference. Now the difference is a very nasty equation that I'm going to write for you. So it is G naught to the minus 1 minus U, commutator with G lesser, minus sigma retarded plus sigma advanced over 2 G lesser minus sigma lesser G retarded plus G advanced over 2 equal to 1/2 the anti-commutator of sigma greater G lesser minus 1/2 sigma lesser G greater. Okay, so this is the quantum kinetic equation. I mean, you can take any electron problem, put interactions, do whatever you want. At the end of the day, you will get something similar. So this is called the quantum kinetic equation. Of course, every product has to be understood as a convolution in general. You have time-dependent coefficients, etc., etc., etc. Then you can ask me, okay, why did you write it in this way and not some other way? Why did you separate the terms in this form? The reason is that I'm going to claim that this is the propagation, and this is the collision integral. And why am I claiming that this is like the collision integral? Because here I have this product, sigma greater, G lesser, sigma greater, etc., etc. Now you remember that G lesser in equilibrium was I times A times F. And G greater in equilibrium was minus I times A times 1 minus F. And therefore, the product of lesser and greater will produce for you terms like F times 1 minus F in general, right? So if you have seen a Boltzmann equation ever in your life, you remember that in the collision integral, typically, you have such objects that tell you what is the phase space that you have for your particles to scatter. So this tells you where you can pick the particle, and this tells you where the particle can go in phase space, right? So that's why you can, almost safely identify this term as the collision kernel. And this term here, well, it's something more complicated because you see that here I have a lesser green function. Well, this term here is going to be a renormalized potential. It's a real part, so it's going to add to your, it's a sort of Thomas Fermi potential generated by the self-energy. This one is a bit more complicated because the distribution is contained in sigma lesser, but eventually it's going to end up in this category. Now, okay, so this is as far as you can go. Then, if you're willing to suffer, you can read the book by Yao, who is using this equation a lot to compute a lot of interesting quantities for semiconductors. But typically, when you write this equation, you have to work on it numerically. Now, it's true that also the Boltzmann equation, you have to solve it numerically. But, at least in that case, you understand very well what you're doing physically. Here is a bit more complicated. So now the idea is, okay, let's look at this equation, and let us try to think about whether we can, in one way or another, simplify it using the fact that we have a separation of scales. So up to here, I never used it. This equation is general. It's valid in all possible cases. Even if you have localized electrons, whatever, you don't have to have a potential that is slowly varying, etc., etc. But now, I want to use the separation of scales. So in order to use the separation of scales, I will have to do two approximations. So approximation number one, I will have, so my G lesser in general is a function of x1, x2, t1, and t2, right? And now I can think of passing two Wigner coordinates both in momentum and in time. So average position, position difference, average time, time difference. So this is x1 plus x2 divided by 2. This is x1 minus x2. This is t1 minus t2 divided by 2. And this is t1 plus t2, t1 minus t2. And now well, if you plug this in here, you can now use the separation of scales by taking the Fourier transform of this equation with respect to omega, to the position difference and time difference, and get an equation of motion for G lesser of P and omega R and T, right? And now the point is that the moment you start doing this, because you have all these products that are convolutions, you will have to go through something painful because you don't know what to do. And the solution to your pains is going to use the gradient expansion again. So every time you see a convolution, you expand in gradients and you go to the lowest non-vanishing order of your expansion. And that is going to be your Boltzmann equation. However, this is not going to be enough because the Boltzmann equation is an equation for a distribution. It's not an equation for something, for a green function. And therefore, so where does the distribution come from? Well, the distribution comes from this, whenever I write it as I times the spectral density P omega R and T times F of P omega R and T actually is a function only of P, as we will see in a second, because omega is constrained. And I make what is known as the quasi-particle approximation. So I say that this spectral density is 2 pi, is approximately 2 pi times delta of omega minus epsilon P minus U of R and T. right? So the idea that is behind this is a sort of, you're thinking of your quasi-particles that is moving in this smooth potential, and the energy is varying as a function of the average coordinates, but you can still define a very good momentum. Now, this is what you would do semi-classically, right? If even though it's not translationally invariant, strictly speaking, if you would think in a Thomas Fermi spirit about the propagation of a particle in a smooth potential, well, you could add, to your energy the potential itself and see what comes and study the shift. Right. So now what I have to do is I have to take this. So step number 2 and step number 1, and plug it in there and try to get something meaningful. Right, so first thing you have to do is to use the gradient expansion. So let me write the formula whenever you have a convolution both in position and in time. So in this case, the Wigner transform with respect to time difference and position differences is going to be A times GR. Well, I shouldn't call it a G. Why did I call it G? I called everything G here. O, let's call it O. R and T, B, where O is equal to the exponential of 1 over 2I of dTA d omega B minus d omega A dTB minus dRA dPB plus dPA dRB. Okay? Yes?
I thought the G-lessness is also from I equation.
Sorry?
The G-lesser has this kind of form when it's in equilibrium.
G lesser has this
IAF.
in equilibrium. Yes, you're right. Yeah, but you remember that when we did the little problem, the one in which, surprise, we got a distribution function. It has 2 steps. So there, I also parameterized f in this way. And what I said is that since it's a non-interacting problem, the spectral density does not depend on the non-equilibrium distribution. The only thing that depends on the fact that you're out of equilibrium is the Fermi function. In any way, bottom line, typically what you do is when you compute the G lesser is you write it formally in this way. This you know what it is the imaginary part minus twice the imaginary part of the retarded Green function. And you identify whatever is staying on the right of it, next to it, as the distribution function. Okay? So that's what you do, right? So it's a way to define a distribution function if you want. I mean, it has the same role in calculations as a distribution function when you're out of equilibrium. What is f? Well, we have to calculate it. We have to figure, so let me put it this way. Let me be mathematically precise. Okay, I want to be mathematically precise. So my statement is that the G lesser there can be parameterized in this form, and where A is minus 2 the imaginary part of the retarded Green function. I can do this, right? Okay. And this, I call it the distribution function. Ipse dixit. So I say so. And I use here only P and not omega because I approximate this as a delta function. And therefore, it's redundant to use 2. Because given the momentum, omega is given. You see, given momentum, r and t, omega is fixed. And therefore, it's redundant to use also omega here. Okay, so now you take this and you plug it in the equation up there. And you have to go through a bit of calculations. Now, let me tell you roughly what happens. Well, first of all, we need a couple of things. If you have an anti-commutator in the sense of convolutions, and you do the gradient expansion of it, so you take the Wigner transform, etc., the lowest order term is the product of the two objects, right? It's twice A times B, twice the Wigner transforms of the two guys, right? Because both the gradient expansion of AB and of BA will start with the term with the product of the two Wigner transforms. If instead I have an anti-commutator, the story is, a commutator, the story is different. Because in this case, the leading order contains gradients. So it's minus I dTA d omega b minus d omega a t dp minus dRA dPb plus dR dPA dRB dRB. Okay, so now I go back up there to that equation and I notice something important. Let's see if I notice that. So remember, this is a perturbative expansion in the disorder in this case. So I am sigma is the result of a perturbation theory. Now, every time I take down gradients, so I have something like products of this type, I will have something like, so this product, for example, will take down 1 over T naught times E Fermi. This product here will take down a term like lambda Fermi divided by R naught, etc., because that's the spirit of the expansion in gradients. Every time you do perform, you do have gradients, gradient combinations, you take down 1 power of your small parameter, which is the ratio of the short length scale to the large length scale. Right, so now I take this and I look at that, and you see something. Well, first of all, you see, compare these guys here to these guys there. So they both have the same ordering perturbation theory in sigma, but the gradient expansion of the commutator starts at first order in the gradients, while the gradient expansion of the anti-commutator starts at 0th order in the gradients. All of this to say that these two terms have an additional smallness in terms of the ratio of these parameters as compared to these ones. And therefore, to leading order, I can neglect them. Okay? So this is step number 1. So neglect these terms. Now step number 2. Step number 2 is I will have these terms like sigma greater p omega, g lesser p omega, and then minus sigma, sigma lesser p omega, g greater p omega. Now, for these guys, what I have is that sigma greater or lesser is equal to this, which is equal to 1 over 2 pi density of states times tau times sum over p of g p greater or lesser. But now I go back to the story I told you before. I plug in here the parameterization that I chose. I times A times F for G lesser, and for G greater, I put minus I times A times 1 minus F, where A is a delta function, is 2 pi times a delta function. So overall, you plug this in this equation, and you will get, for example, that the typical term that will spit out is, well, the combination of these two guys is going to be minus A p omega RT, which is the delta function, 1 over 2 pi mu naught tau, sum over Q, A Q omega RT, and then F of Q minus F of P. So this is what you get if you plug in this expression. This sum over Q is actually what I called here sum over P. I apologize. And, well, this particular combination comes in because, well, you have to do a bit of algebra, right? So here you will have F times 1 minus F minus F times 1 minus F with certain indices. And it turns out that the two products will cancel, so only the single Fermi functions will remain. Right, so you plug this in the equation up there, and what you get is the following. So this is the term that stays on the, why life is so miserable. So that term is the one that stays on the right-hand side. So the collision integral. Yes? Which definition? Those two are neglected. Well, so as I said here, if you have an anticommutator anticommutator in the sense of convolutions of two functions, then the gradient expansion of the anticommutator starts at first order, because the zeroth order is equal to 0. While the gradient expansion of the commutator starts at zeroth order. Now, this means that the anticommutator, if A and B are some functions, right, given functions, the anticommutator is going to be smaller than this one by an extra factor 1 over tau naught times C Fermi or lambda Fermi over R naught, which are small parameters. This one is the anticommutator, this is the commutator, and, well, this smallness here refers to this. Okay? So, and therefore this guy typically is much smaller than this one. If A and B are given, the anticommutator is an additional smallness, and therefore if I want to go to leading order, I can neglect it. I can throw it away. Okay, so now there is one last thing that I have to do, which is I have to take the gradient expansion of the action of that differential operator on G lesser. Well, there is not much need to take gradient expansions there. You just have to do the Wigner transform and figure out the various terms. And if you do the Wigner transform of that term, you will get the following. So let me show you. You will get, so that g naught to the minus 1 minus u acting on g lesser Wigner transformed is equal to a p omega r and t times dtf minus dr, plus minus dru dpf plus dp epsilon p drf, and that is it. Okay? So now you look at what we got. You see we have this combination dr, dp, dp, dr. This comes from the gradient expansion, nothing else. Now I just combine, so this has to be equal to that. All these two guys are gone. And then I have dtf. So dr du minus dr du is the force that is acting on my particles. So f dot dpf plus dp epsilon p is the velocity of my particles, right? So v dot drf. So this has to be equal to, let me not get things wrong, 1 over 2 pi mu naught tau sum over q aq fq minus fp. So you see, well, this is the Boltzmann equation. I'm sure that you recognize it. Now, the fact that you have force times derivative with respect to the momentum of your distribution comes out in this language because we did the gradient expansion and it spits out for us these combinations of derivatives. And similarly for velocity times drf. Well, this one is just the collision kernel for scattering of impurities. You can just check it going to any book. Yes? Sorry? FP is, well, FP, so this is FP, 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 right? So, and this is summed over Q. And this is 2 pi delta function and blah, blah, blah. All right, so you see, this machinery therefore produces, if you do the gradient expansion of your kinetic equation, produces for you well, this. And then you can ask yourself, okay, so what do I do with it? Well, what you can do is you can now take this machinery and use it to study, for example, the corrections, the quantum corrections to the Boltzmann equation, the next order in the gradient expansion. So as I could study yesterday, the next order to the formula, to the Brouwer formula, and see what are the corrections due to non-adiabaticity to that formula. In this case, you go to next order and you have your quantum corrections, right? So, right, so I have another 20 minutes, so I will rush through an application. The final thing I want to say, what is the? Capital F is the force. So the force is minus the derivative of the potential. Right. So, right. So now there is one last thing I want to say that it's a kind of simple exercise you can play with that is also a bit cute. So it's interesting pedagogically, and it concerns essentially the use of all this machinery to study process of dephasing and dissipation in qubits. So now we talk about quantum, and we will get more funding for the next school. Right, so it turns out that the story of dephasing and dissipation of qubits is actually very old. You can read the book by Abraham, which is called The Principle of Nuclear Magnetic Resonance. It's a book written in the 50s of last century, and the whole story is essentially told there. But so how do you define, suppose that I have a two-level system, right? So I have a density matrix, which is a 2 by 2 matrix, and let me parameterize it in this way. So how do I define what is dephasing and what is dissipation? So do you know the answer? What is dissipation and what is dephasing? Right, so when you look at a 2 by 2 matrix at a qubit, this dephasing is actually the decay as a function of time of the off-diagonal matrix elements. So that's why those who want to do quantum computers are scared about dephasing. Because if the off-diagonal matrix elements decay, then you go towards a mixed state. And then you don't have coherence anymore. And then your qubit is useless. You cannot use it. You don't want a classical qubit. So therefore, dephasing, so the off-diagonal matrix elements will typically go like this. And this is the time scale with which, the rate with which the off-diagonal matrix elements decay in time is called the dephasing rate. What is delta F? Well, I'll tell you in a second. So delta F is the imbalance of the population of up and down, of the up and down projections in your density matrix. So the decay of this, people call it dissipation. Or relaxation, well, whatever. Why? Because if this decays in time, you're going towards a mixed state, right? And you're going towards an infinite temperature state. So of course, if you're connected to a thermal bath, you will not decay to an infinite temperature state, you will decay to something else, so you will have to add here something. But in general, for the sake of simplicity, let me assume the decay to an infinite temperature state. And it turns out that the dephasing rate is actually given by, has a relation to the relaxation rate times gamma z, which is where gamma z is called the pure dephasing rate. So let me explain you what this gamma z is in a second with a simple problem. Imagine that we have what is known as the pure dephasing situation. Now, dephasing typically is generated by the fact that your qubit is interacting with the external universe. So you have some photons, something, the cryostat, electrical noise from the wires that are coupled to your qubit. And this is coupled to it, and sooner or later you will see this external world, and this leads to dephasing, this coupling. Here I want to use a simple model of dephasing just to make contact with what I just did a few minutes ago. So my simple model of dephasing is the following. I will say that my Hamiltonian, okay, first of all, I'm going to write a two-level system in second quantization. That is something crazy to do, but you know, I want to make contact with Keldysh, so allow me to do it. So let me write my two-level system in the following way. C dagger I, then delta H of t, sigma z ij, C dagger Cj, right? So I'm writing CR fermionic operators. So you see that if I have one fermion in my, so in the single occupancy, this Hamiltonian is equivalent to the Hamiltonian of a spin half, of course. Now the reason I'm writing it this way is that I will want to use green functions, so I need to put it in the form for which I can use green functions. And now what I'm considering is the pure dephasing situation, which is what happens when you have a longitudinal noise. So in practice, what you have is a Zeeman splitting that is random. It's oscillating in the z direction, and it has, let's say, it has zero average and it has some. It is delta correlated in time, and what I want to know is, as a result of this noise, how a coherent superposition will decay, right? So in practice, what I want to do is I take an initial state, which is psi naught, which is 1 over square root of 2, 1, 0, plus 0, 1. And then I ask myself, okay, so I write the corresponding density matrix, which is going to be 1 half, 1, 1, 1, 1. And then I want to know how the diagonal matrix elements decay as a function of time. Okay? So how do I solve this problem? So there is one simple way to solve it, which is just to write down the equations of motion for your problem. So you write it down, for example. So I'm interested in the density matrix. The density matrix turns out to be equal to this. So is equal to phi naught C dagger J of t, Ci of t, phi naught. So this is my density matrix. And if you think for a second, this density matrix is nothing but minus I times G lesser of Ij dt. Not surprisingly, again, it's the usual story. So let me now write the equation of motion for G lesser. So write I dt G lesser dt. Okay, I want this, tt prime. So what do? I first act on the left, minus delta H sigma z G lesser is equal to 0. And then I act on the right, minus delta H sigma lesser sigma z G lesser is equal to 0. And then I find the function that satisfies these two equations and put the times to be equal. Now, of course, you don't need to use all this machinery to solve this problem, but it's useful to use it to understand the connection. Right, and what you find is that your G lesser tt prime is equal to I u of t, phi naught u of t prime, u dagger of t prime, where phi naught okay, phi naught I'm going to define it as in a second. Phi naught is a 2 by 2 matrix, that represents the initial state. So phi naught here is I over 2, 1 plus sigma x. And the u is, u of t is e to the minus I sigma z integral 0t dt prime of delta h of t prime. Well, now you can put the two indices to be equal, and that's your green function, your density matrix, and everything else. Now, what is the story now? This is because you want me to finish? So what is the story now? The story is, you see that this density, for each realization of your disorder, right? The density matrix, I mean, this green function and the corresponding density matrix is going to have a certain time dependence, right? Now, in this particular problem, which I have, and this time dependence is there is no real dephasing in a single trajectory because the evolution is unitary. However, when you average over many trajectories, then you get an exponential decay. This is called inhomogeneous dephasing. It's like the thing that experimentalists are doing an MRC when they try to use nuclear magnetic resonance to measure something in your head or somewhere, and each spin has a slightly different precession frequency, right? And therefore, they don't see a coherent motion of all these guys, but they see them going out of phase, and when they average, they see something blurred. So something similar is happening here. So now let me take, therefore, the disorder average. I mean the average with respect to the noise. And what I get is I, u, phi naught, u dagger average. Right, so now you write this as psi. Now you have to use, in order to take these averages, you have to use the how's it called, Euler decomposition of these operators. So the fact that e to the minus I sigma z psi is equal to cos psi times the identity plus I sine minus I sigma z sine psi. I don't know, I mean, who's the formula, who does it belong to? Now, you use this formula, and then you use this, you use the statistics to take averages, right? Because these are cosines and sines, so they're exponential functions. And if you have Gaussian statistics, taking the average of an exponential function is straightforward. At the end of the day, what you will get is that this is equal to I over 2 identity plus sigma z e to the minus gamma times t. And if you look at it, this is I times the density matrix. So you see that the off-diagonal matrix elements of your density matrix are going to 0 as a function of time. Okay? So life is very, very simple. So now comes the question, okay, can we obtain this in some other way? So I'm going to sketch the calculation for you. So since I have disorder, I can play the same game I've been playing before. So I write down my Dyson equations, and I will have my self-consistent Born approximation. Again, also in this case, you can prove that it's appropriate to write the self-consistent Born approximation, and it's going to have this form. Yes?
So you should start before. Okay. Like let's say 2 minutes.
Okay, I will finish. I will finish soon. Can I finish in 2 minutes? Okay. So now you take these two things, and now you play the same game we have been playing before. I dt g lesser equal to sigma lesser g advanced plus sigma retarded g lesser, and the same guy for this one. And then you take the difference. And then you take the 2 times to be equal. So what is the equation that you get at the end? The equation that you get at the end is dt rho equal to gamma over 2 sigma z rho sigma z minus rho. And this is what is the Lindblad equation. And the solution of the Lindblad equation is that one. Okay? So I finished in time.